Okay, so hi everyone. I'm gonna be presenting on cryptography, and through this presentation, I will be teaching guys what cryptography is, the concept, as well as the history of how it came to be and like the advancements over time, as well as its modern day uses. I'll also be referring to the relationship it has with computer science, as well as the training or education required to get an occupation in cryptography, as well as the types of occupations cryptography has. I'll also be referring to major milestones within the advancement of cryptography. Okay, so let's get started. Okay, so I'm going to start off by talking about the concept. So the point of cryptography was to improve privacy and to avoid others from intervening between any kind of communication happening between two other people. So it basically improves privacy. So often when someone hears the word cryptography, the first thing that comes to their mind is cryptocurrency or Bitcoin, which is a type of cryptocurrency. So this is partially correct, as Bitcoin is a digital currency which uses cryptography to encrypt transactions that occur on its blockchain. So you guys are probably wondering, well then what is cryptography? Well, cryptography is the concept of encrypting and decrypting data when it is being shared to a specific person or group. This helps keep the prying eyes of hackers from being able to intervene and access this data without you guys knowing. So cryptography is built into almost every application and site we use in our daily lives to help protect our privacy. I'm sure many of you have heard about Caesar Cipher. So for the people who don't, well, that was the first ancient form of cryptography or encryption. Caesar used the cipher to send encrypted messages to his soldiers, and to encrypt the message, he shifted the letters' positions by a fixed number n. Thus, if his enemies get a hold of his message, they would assume it's complete nonsense, or they would be unable to decrypt this message. Anyways, this leads me into the history of cryptography. Okay, so as I said before, Caesar created his Caesar cipher to thwart his enemies from intercepting and then understanding what is put into his messages to his soldiers, as well as the other way around for soldiers to send messages to him. So an advantage that Caesar had during his time was that most people were illiterate, so many of his enemies would be incapable of reading what he wrote anyways. So the thing about Caesar's cipher was, because of that position shifting, many enemies would think that it's written in a different language. But there was actually a vulnerability or a way to break Caesar's cipher, and 800 years later, a man named Al-Kindi actually figured this out. So the method to doing this was finding the letter frequencies of the language which this whatever message it is written in. So in the case of English, its letter frequency is E. So what I mean by letter frequency is that when we're writing anything, for example, let's say a paragraph on how much you guys like math. So in that paragraph, the most frequently occurring letter would be E. So using this, we can determine in a encrypted message, if one letter is like extremely repetitive, we can determine that that is actually the letter E, and using that we can identify the number of shifts that's occurred in the message and then decrypt that message quickly. But this is, of course, it's not foolproof. There's actually like a certain kind of scenarios where this would not work out. But an example is below. So I have an encrypted message. So I'm not gonna tell you guys until I'm gonna give you guys 5 minutes to figure out what this message is actually. So you guys can pause the video and try to decrypt my encrypted message. So hopefully you guys tried this out. If not, that's okay. So here we have a frequency graph for this encrypted message, and as you guys can see, the most frequently occurring letter is L. So using this, we can determine that L is actually E shifted a certain number of times to the right, or it could be to the left. um, but usually the right is much easier to calculate than the left, as the distance between E to L from the right is shorter. Anyways, so when we go in reverse, we know that E was shifted 1, 2, 3, 4, 5, 6, 7 positions from the left to the right. So using this, we can determine that the shift used for this encryption was 7. So using this, I'm able to decrypt the message, resulting in me having my original text, which is like below over here. So I'm going to show you guys another frequency graph. This is to prove my point. So in this graph, this is of the original text, or the decrypted message we got. So in this graph, you guys can also see that E is the most frequent letter. So using this, we can easily see that E is the most frequently occurring letter in like most paragraphs and most scenarios, and so this is one of the simplest ways to break Caesar's cipher. So now I'm going to be demonstrating how two people would use the Caesar cipher as well as the Polyalphabetic Cipher along with the Onetime Pad. I will also be demonstrating how two people would share the key before using the Onetime Pad to encrypt their message, and how they keep the man in the middle, or the person trying to get the key or the data that's being transferred between the two, how they're hiding that key from that person. So I'm going to start off by explaining the Caesar cipher. So over here, let's say there's a person A, and we'll make person B blue. So person B is over here, and then someone will give the name as intruder, or a better name for them would be interceptor. So person A wants to send a message to person B. So let's say that message is just hi. So person A will encrypt that message. Let's say they shift it by 1 position, just a simple example. So H becomes I and I becomes J. So then person A would send this message over to person B, and then person B would use IJ and they would also need to receive the shift value, which in our case is 1. They also need to receive this. So the thing about during Caesar's time was that his soldiers already knew about this shifting and the shift values and so on. And so Caesar did not have to worry about the man in the middle intercepting or learning about the shift value. So we're just going to assume person B already knew that the shift value was 1. So now person B will easily decrypt this message and figure out it says hi. And if the man in the middle or the interceptor were to intercept this message in between, all they'll be getting is IJ, and they'll be wondering what it means, because they don't know the shift or like what was used to encrypt it. Okay, so this was just a simple example of the Caesar cipher. So now I'm going to move on to the Polyalphabetic Cipher. So let's move on. So for this one, we have another person A, another person B, and we have another interceptor. So this time person A wants to send hello, but they know that the Caesar cipher is not strong enough to hide their message, so decide to use the Polyalphabetic Cipher. So what the Polyalphabetic Cipher is, so basically what this Polyalphabetic Cipher is that we would choose a secret word. So let's say person A chose
let's just say bat. Okay, so the position of B in the alphabet is 2, the position of A in the alphabet is 1, and the position of T in the alphabet is 20. So what happens is person A would take this word, shift first H, which H's position is 8. So you take 8 and you add 2, which is this value here. Then you would take the E in hello, which is the next letter, and which the position of E is 5. So 5 plus 1. And then L, first L, you take that and you would add 20 to its position, so the position of L is so it's 12, so it's 12 plus 20. So now the new position of each of these letters would be 10 for H, 6 for E, and 32 for L. So I think I didn't mention this during the Caesar cipher portion of this. So what happens if you shift over 26 is that it starts again. So after 26 you start from A, so you basically go back to 1 and so on. So in this case the position we got was 32, so we can just subtract 26 from 32 and we get 6. So the new position for L is 6. So what happens here is now H becomes J and then E becomes F and L also becomes F. So now what person A has to do is they have to share their secret word along with their encrypted text or message, but they would send this secret word earlier. So the thing that the only small issue with this was that if the sender were to figure this out, because they can all of course intercept whenever like the secret word or the text was sent. So I'll be explaining how they do that without the sender knowing a little bit later on in this video. So we're just going to assume the sender does not know about the secret word, and that the secret word was shared only between person A and B. So person B receives the secret word, which is bat, and then person A sends their secret message. So hello is sent to person B. So now all person B has to do is take hello and reverse the letters. So I didn't do each and every letter here because I didn't want to go through the whole thing. So I wanted to give you guys like a simple understanding of what I meant. So that's what happened. So after doing bat once, since bat is only a 3-lettered word, I would start over again. So for the next second L, I'd use B, and then for O, I'd use A, and like so on. You just repeat that for your complete message. So now person B can easily decrypt hello. Of course, it's not going to be sent as hello. It's going to be sent as the encrypted version of this. So I'm just going to write this because this is all encrypted. So person B would be able to decrypt this using their the secret word that they got. So I only wrote HEL because those are the 3 letters we encrypted, but I'm pretty sure by now you guys got a simple and basic understanding of what I meant by the polyalphabetic cipher. So now let's just say the interceptor were to intercept this message. Even if they receive the message using the concept of letter frequency, they would still be unable to figure this out, because what happens now is, because you have multiple shifts in this situation, the interceptor would struggle to figure out which shifts are used for which letter. But over time, you could it would take quite a bit of time, but you could still figure out the word used to shift these letters. And if they were to figure out the length of the word, so let's say they figured out it was a 3-lettered word, all they have to do was check out of every 3 letters, the first letter there, the last and second, and like they can take them all individually, and then they can use Caesar ciphers, the method to break it, the letter frequency, and they can use that to decrypt the message. So that's the reason, even after we moved on to the polyalphabetic cipher, we had to find another more secure encryption method, which we created as the Onetime Pad. Okay, so the Onetime Pad, I mentioned it multiple times, but I'm gonna explain it now. So the Onetime Pad, let's just say it's person A again, and then person B over here. So as I said before, the secret in the case of the Onetime Pad, it's a secret string of numbers. I'll explain that a little later on. But just like the previous 2 examples, we're gonna assume that this was shared without the interceptor knowing. So let me just write interceptor here, and then so this string of numbers, let's just say the text is world. So what person A would do is, when they're encrypting it, they would encrypt it at complete random. They'll choose random numbers to shift each letter back. So let's say they chose 1, 2, 3, 4, and 5. They won't, realistically, they would not choose like 1, 2, 3, 4, 5 in order. It would be actually random numbers, completely randomly generated, because that's how the Onetime Pad works. When you use random number generation, then what happens is, even if someone were to do a frequency analysis for the letters in your message, all the letters would have literally like a equal amount of showing up like frequency in that encrypted message, that you can't decrypt that. So that's why the Onetime Pad is the best method for encrypting. So all person A has to do now is send their little string of numbers to person B. So we're gonna assume that person B already received the string of numbers. So person A encrypts their world with this encryption. So W becomes X, O becomes PQ, and R becomes STU, becomes U, and then L becomes MNOP, and then D, E, F, G, H, I. So this is a new encrypted word. So this is what's sent to person B, and the interceptor can intercept this one. But person A won't mind, because even if the interceptor does intercept this message, they would be unable to encrypt it, as they know that, as person A knows that the string of numbers which encrypt their message was already given to person B. So we call the string of numbers, or the secret word, and the shifts, those are actually called keys, because they're used to decrypt a message that's encrypted. So what person A did was share the key earlier to person B, and then send the message. So now that person B has the key and the interceptor doesn't, person B can easily decrypt the message, but the interceptor cannot decrypt the message because they don't have this key. So this is why the Onetime Pad is the best method of encryption. So here comes the issue of, so how do we share this key privately without the interceptor interfering and figuring that out? Because then if we were to send a message, the interceptor would easily decrypt our message. So I'll explain that. So I'll explain that a little later on. So this is basically the 3 different examples. If you guys want, let me know in the comment section. I could actually post this in my description, or any other aspect of the video. If you guys want for example, the code in like a text format or something like that, you guys just let me know in the comments. I'll add that. So as I said, now I'm going to start talking about how person A and person B would share their public key, which they would publicly share, but person A and B would still be able to send a message and decrypt each other's message, but the person in the middle who got the public key would still be unable to figure out what the number was or decrypt the message. So I'm going to show you an example. So person A is over here. We'll say person B is over here. For now, we'll just ignore the interceptor, and I'm just gonna talk about what person A and B do. So person A chooses a number, let's just say 13, and person B also chooses a number. Let's say person B chooses 15. So now what they use for sharing a public key is actually the modulus. So they choose an expression, you can say. So the expression would be, they would choose it would be n mod m. So publicly, person A or B would share the n value and the m value. Okay, so in the case of this question, so for this question, we're gonna say the n value is 3 and the m value is 17. So they publicly share this expression. So they share 3 mod 17. So this is publicly shared. And so now we can look at the interceptor. So interceptor is here. So the interceptor has access to this all this information, as well as person A and B. So now what person A would do is they take their number, they'll do 3 to the power of their number mod 17 and find the value that's equal to. In this case, it's 12. And similarly, person B would take their number, and person B would do 3 to the power of their number, which is 15, mod 17, which is equal to 6. So now person A would share their answer value, which is 12, and person B would also share their value, which is 6. So now the interceptor also has access to these. So also person A has access to 6 and person B has access to 12, but the interceptor also has access to these numbers. So now what person A would do is they would take person B's answer that they shared publicly, which is 6, raise it to their own private number, or the number they chose. In the case of this is person A chose 13. They would mod that by 17 and find the value they get. And in this case they get 10. Similarly, person B would do the same. They take person A's answer value and raise it to the power of their private number, which is 15, and they mod it by 17 and they get the same number. So now the secret that the two people were sharing was 10. So this is how one would share the key early on without the interceptor knowing, with the interceptor knowing the key, but the interceptor would be unable to decrypt any messages going between the two people. So you guys are probably wondering, well, how does this work? Well, what this is basically, let's show this. So this is basically 3 to the power of 13 to the power of 15 mod 17. Okay, and when you look at the other side, person B is 3 to the power of 15 to the power of 13 mod 17 is equal to, in this case we got 10, but so this value here is the same as 3 to the power of 13 to the power of 15 mod 17. So now you can see how these two numbers would give you the same value. So because of this, both person A and person B end up with the exact same numbers. So this is how one would share their, I guess you would say this is the key for their key publicly, and then this would be used to get their data. So that's how this public key and interceptor idea works. So now what we're going to do is take this and put it into proper a context. So Euler, who was a famous mathematician and physicist, so he figured out this expression called phi. So if you do phi of a number, what it does is it goes through every single number that's from 1 to the number itself. So let's say we chose 8. It will go from 1, 2, 3, 4, 5, 6, 7, 8, and it will select the numbers which don't share factors with 8. So in the case of 8, it would be 1, 3, 5, and 7, as those four numbers don't share a factor with 8. So another thing you guys may be wondering, but 1 does share a factor with 8. You look what phi looks at is the numbers that share a factor of 8 that are greater than 1. So we include 1 when we're looking at the answer for phi. So phi of 8 would return 4 because there are 4 numbers that don't share a factor with 8. So similarly, the reason that phi of 8 returned 4 was because it was a constant number. But if you had a prime number, what phi of a prime number would return would be the prime number minus 1, because the prime number shares a factor with itself. As you guys know, I explained that it goes from 1 to the number itself when phi is checking factors. So if I did phi of 31, for example, then 31 has a factor of 31. So because of that, 31 and 31 share a factor. So you subtract 1 from 31, resulting in 30. So phi of 31 will give you 30. So similarly, if you do that with any kind of prime number, or phi of a prime number would equal the prime number minus 1. So we'll be using this and Euler's theorem, factor theorem. We'll be using this to help us out with our encryption of our data. So I'm going to show you guys another example. So we're going to write person A again. So this is person A. You'll have person B. So this is called actually a trapdoor method. So person A will choose two numbers and they're both prime numbers, so P1 and P2. So let's say person A chose 53 and 59. So now, as I explained before, phi of a number or a prime number would result in the number minus 1. So now we're going to do n. So n is equal to 53 times 59, and then we're going to do phi, this is the symbol for phi, n is equal to, and we get the result of 3016. Then we choose a random number e, which is, you can assume as the encryption number. So we say e is equal to 3. So to find the decryption number, or the number we're going to share to person B, we'll be needing this expression. We'll take 2 times 30, 16 plus 1 divided by 3. This would result in 2011. And what we'll do is share n and the d value. So we're gonna give person B the n value and this d value. So now what person B will do is, if they have some sort of message they want to send or anything, they'll use the n and d value. What person B would do is, they would take the n, oh I'm so sorry, I made a small error over here. So they don't share their d value, it's actually the n and the e value that's being shared. So what person B does with this is, they choose some number, let's say m, let's just say they chose 89. So now what happens is, what person B would do is take their number, raise it to the power of e, then mod this by n. And in our case, we use n as 3127. So the value of this would be what person A would get. So this should be 94. Okay, so this number, we'll go here to A. So what person A would do is, they take 1394, raise it to the power of their d value, in our case was 2011, and then mod n, which is 3127. This would be equal to 89, which, as you guys already know, is the m value which person B had. So this is how they shared the secret. So now let's look at this from the perspective of our interceptor. So interceptor. Okay, so the interceptor was able to get the n value, the e value, and they were able to get the, let's just say this is the c value, 1394. Let me just write that there so you don't get confused. So we say that c is equal to this one. Okay, so as you guys can see, without the d value, the interceptor cannot decrypt the number 1394. So this is how encryption works. This is the proper how encryption works in like our daily lives and everything. So when you're sharing something from one person to another, so this method, what happens is that person A shares, I guess you can say, the lock itself to person B, and person B would lock whatever they're sending to person A with using that lock, while person A has the key to the lock. So that's how this basically works. So this is to give you guys a basic understanding. I did skip a few details for this, such as explaining what Eulers Theorem is and so on, but I have very little time for so because our videos are getting pretty long. But if you want more detailed videos, please let me know in the comment section, and I will try my best to give a more detailed video next time.
Okay, some fun facts on cryptography. So, yes, as of now, as I said, the Onetime Pad and methods like that for encryption are the best and unbreakable. The reason behind this is because even if you had all the power, computing power, on Earth, you would be unable to decrypt those encryption methods. It would require thousands of years, but um, a new kind of computer called the quantum computer. People are starting to get huge breakthroughs in these, and these quantum computers use qubits, and they work a little different from our regular PCs or supercomputers and so on. So some um, questions or problems that even supercomputers can't solve, quantum computers can. But then another thing is that some simple basic problems which our computers can handle, quantum computers can't. So the thing about quantum computers is you can actually use them to easily decrypt anything that's encrypted using the Onetime Pad or any of what we're talking about, any of the encryption methods we talked about. Because if we look at our everyday lives, our PCs, we use bits, and what happens in the case of quantum computers is that they use qubits. So in the PCs, the smallest number is 2, the smallest value the computer understands, 2, it's on or off. But in the case of a qubit, it's on, off, and then there's the state in between, which is like basically when it's on and off at the same time. So there's 2 states like that. So it results in when you're looking at the number of qubits compared to a bit, 2 to the power of the number of qubits. So a better way to understand this could be, so the maximum number of atoms in the observable universe, as in the universe that we can see so far, is actually only between 10 to the power of 78 to 10 to the power of 82. So that's the maximum number of atoms that as of now we know exist, because this is how far we've seen into the universe and so on. So when you look at this, and let's say we have 300 qubits, to get the value of 300 qubits, you'll need 2 to the power of 300 regular bits. That's equal to 2 times 10 to the power of 90. So you guys can see right there, 10 to the power of 90, that's larger than this. So we need more atoms, because in the case of bits, and you compare them to atoms, so you need more atoms than we can currently see or know of if we wanted 300 qubits worth of bits. So that's an example showing how much more powerful and advanced a qubit is. So in the case of cryptography, as I explained before, what happens is because of this, quantum computers are capable of easily decrypting or breaking the encryptions we have as of now, which we use in our daily lives. So if, for example, even Bitcoin, the blockchain is, as of now, you can't hack it due to the encryption, all that stuff. You can't hack and get Bitcoin, because even if we had all the computing power on Earth, we would be unable to do that within, like, it would take approximately about like 1,000 to 2,000 years if you were to try with all the computing power we have on Earth. So when you compare that to a quantum computer, if you had a quantum computer that's capable of 300 qubits, a 300 qubit quantum computer would be capable of easily breaking those things, encryptions. And so the blockchain will easily hacked, and so if a quantum computer were to go into wrong hands, there's a really high chance of many illegal activities occurring, and it would be really hard to stop these kind of things because we'd require more quantum computing. Luckily, quantum computing is currently in the early stages, so quantum computers are not widely available, and the only way for regular people to access them would be through the cloud. So that's basically why quantum computers are very capable of destroying the encryptions we have now. So if someone were to get a hold of a pretty decent quantum computer, they would be easily able to crack into the Bitcoin blockchain and make millions of dollars a day, simply. So yeah, that's a fun fact I felt I like sharing. Um, I could go more and more into quantum computing as it's a pretty broad and very interesting topic, but I think that would extend this presentation way too long. So I'm gonna possibly create this in another one of my presentations. So don't worry, soon I'll be uploading another video that has to do with quantum computing so you guys can get a better understanding of what quantum computing is and how quantum computers work. Okay, so now I'm going to talk a little bit about education, then I'm going to start on careers and occupations. So, usually when people study cryptography, they aim to become a cryptographer if they want to specialize in cryptography. But programs such as computer science and even sometimes computer engineering would have cryptography as a mandatory lesson or somehow integrated into the course or program. So even computer engineers and computer scientists would learn cryptography, so they would have some knowledge regarding cryptography, encryption, decryption, and etc. I'll get into the relationship between computer science and cryptography a little later on in this video. For now, I'm just going to talk about this. So now the careers and occupations, usually when you want a career in cryptography, generally become a cryptographer and you work for government agencies or private agencies who work with encrypting and decrypting data. So in the case if you work with like the police or the FBI or whatever, they would want you there to either encrypt their servers or decrypt some kind of data transfer that's happening which isn't legal, or they need that data, they would ask you to figure out how to decrypt it or to find new vulnerabilities. So that kind of stuff with the police and government wise, basically encrypting their servers, whatever they do, all that. If you're doing a private or some sort of private company or anything hires you, then it's probably for, like, let's just say Amazon. Amazon requires a lot of encryption on their website and everything, so to keep hackers out from hacking in and, like, first of all, destroying the website. Second, hacking and stealing people's credit card information and stuff like that. So all this stuff requires some sort of encryption to keep your data safe. So when you input your credit card, you know that no hacker is gonna just hijack it from there as soon as you type it in. So stuff like this is what people who go in the cryptography field deal with and try to encrypt or decrypt. Create sometimes they even create new algorithms or encryption methods. So the kind of degrees that people would pursue in the case of becoming a cryptographer would be either a bachelor's in mathematics, a bachelor's in computer science, or a bachelor's in some other related field. I guess computer engineering also falls under this. So mostly people who wants to be successful, like, and do really well in the cryptography field and want to be, like, hired, like, really quickly, they would pursue a master's or a doctorate degree. So then after that, what most people do is work as an intern, and after that, then once they gain some experience and stuff like that, then they'll properly be hired by other companies. Sometimes if you do extremely well, like outstandingly well, other companies could hire you. So another thing about this field is salaries. So the average salary of a cryptographer as of 2021, according to multiple sources, is 149k, and this is just average, but the entry level cryptographers can get between 104 to 109k annual salary, and then the higher end, or like the really the more experienced and more outstanding cryptographers generally make between 189k to 197, sometimes even 200. So if you were to go in a cryptographer field, it would be pretty rewarding in the financial aspect, but it'll also be kind of stressful when you're working, because you'll be put pressure by you'll be given pressure by the company who's hired you, or the government, or whoever it is, to have time frames that you have to manage. So it's not a really easy field, but it's pretty rewarding if you know how to do it and if you're really good at it. If you guys have any other questions regarding like the careers, education, and stuff like that, you guys can just put that below in the comment section and I'll answer it as soon as I get some time to. So some skill sets. So some people are probably wondering what some skill sets for cryptographers are. So advanced algebra, algorithms, of course, like I explained and showed before, programming languages such as C, C++, Python, and Java. These four languages are very important when it comes to actually putting the cryptography skills that I explained to you guys in a more mathematical form. When you're putting into a real life situation, you'll require these coding programming languages. Then you also need to gain skills in symmetric cryptography and asymmetric cryptography, as well as computer networking and cybersecurity. So these are some major skills, but what I'd recommend is mainly focus on your math skills, as cryptography is the basics, and most of the advanced is mainly based on math, as I've shown and explained to you guys. And the only difference that has in real life is that you're going to be integrating some programming languages along with your mathematics skills. So yeah, math is probably the best and most important skill for a cryptographer. Okay, so the relationship between computer science and cryptography. Um, Cryptography is something, well, in the way I spoke of it, I spoke in a more math kind of concept, but that's to help you guys understand what it is. When you use that in with the data being transferred instead of numbers, that becomes basically what happens in our everyday lives. So, like for example, for accessing a website and logging in, let's just say YouTube or Gmail or something like that, if you sign in with your username and email account, password, your name's usually with your email and etc. All that stuff, data being sent to the Google servers and received by your computers from the Google servers and so on, all that has to be encrypted. And basically the math method I demonstrated to you guys is used in a more computer modified for computers kind of way, so that data is encrypted and hackers cannot in between the data transfer process, they can't intercept it and understand what's in that encrypted message. So that's basically what has to do with computer science, because it takes both skills from computer science and mathematics. I showed more mathematics like I said, but it takes both skills, the coding aspects of computer science as well as the theoretical aspects of computer science, along with the mathematical algorithms and um, arithmetic sequences and etc. Putting those together is what forms the heart of cryptography, and that's what makes it so important in computer science as well as computer engineering, as most computers would be communicating on some sort of network or communicating to a server, like whether it's peer-to-peer or peer-to-server, however it's transferring data, it would require an encryption unless you're okay with other people intercepting whatever you're sending, stuff like that. So I think I showed near the start of the video a picture of someone texting their parents. So something like that would have to be encrypted. If it were not, then hackers would know what you're sending and stuff like that. So it's a lot of both privacy as well as a security measure for us, and it helps us stay safe from hackers, as well as other people want to gain access to our data or know what we're doing, or who want to steal information which could be valuable to them in ways of making money and so on, but it can be even more valuable to us. Even identity theft and stuff like that occur due to poor encryption methods and stuff like that. So that's how cryptography and computer science have a relationship, because you'll need to know both coding as well as mathematical aspects to actually become a cryptographer, and you learn that in computer science. You'll learn algorithms, mathematics that's integrated into coding and programming, and when you put all those skills together, you basically have the skill sets for a cryptographer. So that's about it for the relationship between the two. Thank you for watching this video presentation, and I would like to give credit to Khan Academy. It's where I learned most of this. So if you guys find that I was not detailed enough, or you guys would prefer another perspective on cryptography, I would recommend you guys go under the computer science in Khan Academy and check out the cryptography lesson, and there are a lot of interesting stuff under there. So yeah, thank you for watching.